Okay, thanks for the introduction. Well, yes, much information is only available in textual form. Think, for example, of books or newspapers or all the web content that is out there, like Twitter data, Facebook, customer reviews on Amazon and all the other stores, and all that stuff. So just to give you some numbers, in 2003, the University of Berkeley published a study that says that about 25,200 and something different newspaper publications are out there, 80,000 mass market and trade periodicals, more than 37,000 scholarly periodicals, and 950,000 new books per year. And this does not cover web content. That is, of course, much more difficult to get numbers for that. So obviously there's something we need to care about, text data as well, and this is what this talk is going to be about. So there will be three main parts. In the first part, I'm going to talk about the challenges of document visualization. Next, I'll tell you something about the automatic pre-processing that has to be done. And in the third part, I'll show you some examples for visual document analysis. Okay, in the last talk, you've already heard the term pre-attentiveness, and I want to dig into that a bit at the beginning. So actually, what is meant by pre-attentiveness is that, there are some basic units of visualization. I don't know if you've heard about that yesterday in the foundation session. So for example, there is shape, color, orientation, all that stuff. And some of these features are pre-attentive, which means that you can grasp a difference, like on that slide, that there are rectangles and there's one circle in the middle. You can grasp that in less than 200 milliseconds. And I would like to do now a quick experiment with you. So I'm going to show you a slide like this, and I'm going to show it to you for half a second. And I would like to pay attention to what is going on there. So if I would show you this slide, then you should tell me at the end, okay, there were many squares and there was one circle in the middle, okay? Are you ready? Then, okay. Please raise your hand if you think that you've seen what is going on here. Okay, that's most of you basically. So let's try it again. Ready? Oh, sorry, that was what you should have seen, and now the new one. Got it? Great. So that's what you should have seen, and now one more time. And go. Please raise your hand if you think you got it. Okay, great. 2. Can you tell what was going on there? Okay, that's one thing, yeah. You did. Sorry? So you saw a single example, but did you see a pattern? Did anyone see a pattern in that? There was a very, very strong, a clear pattern. Okay? I'll show you that slide again, and now I don't remove it anymore. And I would like to ask you to raise your hand as soon as you think you know what is going on. Okay, first hand is, 3, 4, 5, 6, 7. Okay, so now you're starting to get it. So it's quite easy actually. Here, all the words are readable. They are spelled the right way, and here reading is going from right to left. And there's a clear, here's in the middle. We have two sides of that. It's like mirrored. Okay. But the point here is that text obviously clearly isn't pre-attentive. You really need to read. You need some time to see what is going on. So obviously, text itself isn't a very good visualization that you just can see something at a glance. So we have to find another way to visualize text, obviously. One way is to represent it with pictures. So that works quite well, actually. Let's try to make it a bit more complicated. It works still. That's fine, I think. Now we can also combine that and have a combined picture. But what about that one? So it seems that with normal pictures, we also quite quickly get to the point where this doesn't work anymore. So let's summarize that a bit. Okay, we've seen that text is not pre-attentive. Second, it's abstract, so it's quite difficult to visualize. It has a very high dimensionality. We have tens to hundreds of thousands of features, so think of the different words that we have. And to make things worse, these features, these words can be combined in innumerable ways. So that's one thing that makes natural language very powerful, but also very challenging for computers, that it's so flexible in the way that you can combine it. And it's subtle, so even small differences matter. This is something that you know if you are, like I'm now talking in a foreign language, and that's not easy always, so I might miss some subtle differences or details. And this is why, if we want to do document visualization or document analysis, this is usually a multi-step process. So there is no, or almost no, I know of none actually, visualization that would really visualize text directly. You always have some pre-processing step at the beginning. So one thing that you have to do is to get that somehow into features, to extract features. These here are statistical, structural, syntactic features. And this is then something that you can already visualize. I'm going to show you some examples for that. And but you can also do have an intermediate step in which you do some advanced analysis and do some feature engineering, for example, to get higher level features, apply text mining techniques like clustering, or do an automatic search for patterns, and then you get the power of the machine more involved, and then you would go to the visualization. And of course, as it is usually done in a visual analytics process, you also have those feedback loops that go back and trigger the machine, the automatic algorithms again. So in the second part, I would like to talk exactly about this. And let me add here that I'm going to talk about the first part now, about the feature extraction part, and not about the analysis part. That would cover stuff like text classification, text summarization, opinion analysis, and so on. These are advanced text natural language processing algorithms, which would be too far for this hour that I have here. Too much. Okay, this is an outline. So we have basic text processing, tagging and parsing, context representation and topic modeling, and information extraction. And let me say here that this is something that you could take a whole course on in a university. And you could even take a course on just parsing and tagging if you are if you're studying computational linguistics. So there's no way that we are going to cover this in this hour. What I'm going to do, and what I would like to do, is just fly over these concepts just to make sure that you've heard of them, so that you know that there is something that you should pay attention to. And afterwards, I'm going to give you some pointers to tools and to literature that you can consult if you would like to continue reading on that. Okay, first, basic text processing. Before we can do anything, we have to tokenize the text. That means to get a list of tokens, like, for example, single words. And the simplest approach for that is that you use white space and split always in every position where there is a white space. But if you look at these two examples there, then you immediately see that it's maybe not that easy, because, for example, what are we going to do with I'll? Should this be, if you just use white spaces, then we get this as one word. But you would probably say, well, this should be I will, so two separate words. Then, next question is, what are we going to do with New York? Is this New and York, or should it be one phrase? And what about something like aluminium export ban? Is aluminium expert one word because it has a dash in between? Or should it maybe even be aluminium expert ban? Because this is what you need. So it's not as easy as it seems, but there are algorithms out there. What they usually do is, I think the smarter ones might get the New York thing, but most of them would split really, use the white spaces. Okay, then two things that you should know as well are lemmatization and stemming. Lemmatization, what it does is that it transforms all words into their basic form, into the lexical form, the form that you could look up in a dictionary, basically. So visualize would become visualize, visual would stay visual, and visualizations would become visualization. Stemming, on the other hand, is gets you the root of the word. And the root of the word visualize, visualized, visual, visualization is all visual. Okay? And now to make things a bit more complicated, these words are, the way that I explained it to you now, this is the proper computational linguistics explanation, but sometimes these words are mixed up together, so that makes it a bit difficult. And the thing with stemming is that some stemmers have a quite funny way of stemming some words. For example, a Porter stemmer is a very famous stemmer that is used often for text mining. And it stems you words sometimes in a really strange way. For example, libraries, you would get library with an I at the end instead of a Y at the end. But this algorithm is quite consistent, so if you give it the word library in singular, then it will also give you library with an I at the end. So if you show that to a linguist, they are like, what is this algorithm doing? We can't work with that, okay? But if you, as a computer scientist, just want to use that in your text mining approach, and you just want to use it for classification, then you don't care about it. So it really depends what you want to do with it, which algorithm you have to choose. Okay, second thing is tagging and parsing. Part of speech tagging just means that you get actually the type of word for every word here, which is, for example, JJ would be an adjective, and N is just a noun, CD would be numbers, and so on. And it depends on the tag set that is used by the tagger, how fine granular this is. On the other hand, we have parsing, and here we have to distinguish between shallow and full parsing. On the right side, you can see the result of a full parser. And as you can see now, here at the bottom, we do have the part of speech tags that we also have up here. But the full parser additionally gives us the syntactic structure of that sentence. So you can see now that, for example, the current account deficit forms a noun phrase, or that we have a subordinate clause here in the second part. In contrast to that, the shallow parser still gives you the flat structure, but it's grouping, again, noun phrases, verb phrases, and so on, which can be very useful. And one thing that is important to understand here is that most full parsing algorithms, at least the ones that work well, can be really terribly slow. So you just want to apply that if you really need exactly that output, if you need to have that. Next thing is TF-IDF. I think that at least some of you probably have already heard of that. That's, I think, in terms of text processing, this is one of the most important concepts. It's about representing documents in vector space, and you need that, for example, if you want to apply text classification or text clustering algorithms. But it's also used for information retrieval. And in that vector space, the terms are the axis, so the dimensions of that space, and documents would then be points and vectors, or vectors. And it's important to know that the order of the words is not taken into account. This is why it's often also called a bag of words approach. And there are two main components, actually, of the weighting, of the term weights. The one is the term frequency, assuming that the more frequent is a term in a document, the more important it is also for this document, which kind of makes sense. But on the other hand, you can think, do you really think that the most frequent terms are also the most characteristic ones? And this is like, well, not always, because the most frequent words will always be like is, the, and so on. And these words are basically saying nothing about the document itself. Okay? So we have that second factor in at the end. This is the inverted document frequency that tells us in how many, so document frequency means in how many documents of the corpus is that term in, and we invert it because we say that terms that are in fewer documents are probably more discriminating for this document that we have. This is why we have the inverted factor in here. And the logarithm is simply there to dampen the effect a bit. You will see this is not the only formula that you get for that. So the basic idea is really to have term frequency and inverted document frequency. And you sometimes see it without the logarithm or with the logarithm, and there are all different sorts of variants. It's just important that you get the basic idea. So this is one straightforward idea how to get your documents into a vector space. Then just a brief comment on the letter 2 here. So co-occurrences, looking for co-occurrences can be very interesting in some applications. If you do that, then in some situations you might want to look at if this is really, if the co-occurrence is really significantly significant. So if the words co-occur significantly more often than you would expect that statistically. And you can use, like, for example, chi-square or something like that for that. An interesting concept for topic modeling is LDA, but I'm not going to discuss that here now in detail because I will talk about that later. And then we get to the next section, information extraction. I'm not going to cover that at all here because I think we have a whole lecture on that afterwards. Here is the list of tools that I mentioned. As you can see, there are some general text processing toolkits that often, so for example, I know the DK Pro toolkit that is simply, it is kind of unifying different kinds of these, the ones that you can see down here, that you can also access as a single tool. So you can get all, if you use these toolkits, then you can get all at once. That's the idea of them, but you can also choose really one of them if you need a specific one. And here's a list of textbooks that I can recommend. And of course, it's important that you have some background on that as well if you want to do document analysis, because otherwise you can't make informed choices simply on which algorithms you take. So even if you don't want to do research in that area, but also for applying algorithms, you need to know a bit about it. Okay, that was this part, and now I get to the third section of the talk, which will be the longest one, with examples of visual document analysis. Okay, so what have we done so far? We've got our documents. We have done some automatic pre-processing or processing of the documents. And now we would like to visualize them. And there are different visualizations, actually, depending on how much structured our data is after this pre-processing step. Because sometimes you really get numbers out of that. And if you do so, then you can use bar charts again, or just the simple visualizations that you would also use for statistical data, of course. In some other applications, it might be the text properties are still important, so that you really need something special, the special characteristics of text. And then we would be on that side of the scale, where we need special algorithms for visualizing our text. And there's another way of classifying this. So this is more the tasking or goal-centric view. And this is that you can say, okay, there are techniques for summarizing or analyzing documents or whole corpora of documents that we have. We would like to look at the distribution across the document of some text property. Then we would need some special techniques, or maybe we would like to show relationships within or among documents, or a temporal trend. And this is now also basically the outline that I have for the remainder of my talk. So I will show you 1 or 2 examples for each of these 4 categories. First one is summarization analysis of documents and corpora. And here again, I think it's the 3rd or 4th pointer to expire. So I don't want to talk about that because we'll have a session on that in the afternoon. But I would like to talk about an application in which we were using actually the proceedings of VASS, SIGGRAPH, and InfoVASS. And our analysis question in this case was, what distinguishes those 3 conferences, or what do they have in common? And if you know that field a bit, then you know that all 3 conferences somehow get visualizations, get images on your computer screen, okay? So that's obviously something that they share. But the interesting thing is still, what is the differences between them? And what I did here is that I first simply plotted them in the word cloud, the whole corpus, and what word clouds do is, by the way, here has been a lemmatization algorithm has been applied before this was done. As you can see, we don't have visualization and visualizations, but we only have the singular form of everything and just the present tense of the verbs and so on. So this was the first pre-processing step that has been done, and then this was thrown into, I guess this was Wordle simply. And now, so the size of the word tells you something about how frequent that word was, and color is simply random. Position is random as well, by the way. So if you look at these word clouds, try to find out what they have in common and what the differences are. Try to make up your mind on that, please. So I think it's not that easy, actually, with visualization like that. So first of all, we again have the situation that we have to read, but this is always the case with word clouds. But still, it's quite difficult to compare that, actually. And the second question that might be a bit out of context here, but just, is this with a visualization at all? It's a question that some people are asking, actually. And I think the community is a bit, is disputed. Some people say it's not a visualization, others say yes, it is one. Exactly because of these issues, because just having words is not pre-attentive, and also because word clouds have their issues in terms of, for example, words are taken out of context and can happen very easily, that you make up a context that is not there and so on, just as a side remark. But okay, so what are we really interested in? Well, what we are really interested in is that we would like to, if we have 2 papers of conference A and conference B, we would like to find topics that are characteristic for conference A and discriminate the collection from the papers of conference B. This is one thing that we are interested in. And note that I didn't say we want to know the words, we want to know the topics. That makes a difference. Second, we would like to get the topics that are characteristic for conferences A and B and discriminate the collection from the papers of conference C. And third, we would like to get the topics that are characteristics for all 3 conferences. I'm going to talk about now how we did that. So the first question is, how do we get the topics? And now we get to LDA that I already mentioned before. LDA is a technique that assumes that documents are mixtures of topics, and topics are probability distributions over words. So in this example, you've got 2 topics at the left here, that, as you can see, are like a bag of words, the topics. And you have documents at the side as an example. And you can see that they are probability distributions over the topics at the left. So for example, document 1 is 100%, has just 100% topic 1. And you can see that so money, bank, loan, bank, money, money, bank, loan are all coming from topic 1. Whereas document 2 is a mixture between the two, 50% of each. And now we are drawing randomly, basically, for each. So for each word, we would first decide which topic to draw something from, according to this distribution, 50-50 in this case. And then we would randomly draw one of the words. And one thing that you can see here as well is that one word, in this case bank, can also appear in multiple topics, because the idea is that it could have multiple meanings. So in the first topics, we have bank in the context of money, loan, and in the second topic, we have it in the context of stream and river. Yeah.
Is it just latent semantic analysis?
Sorry?
Is it just latent semantic analysis, or is it something different?
No, that's something different. Yeah. Okay, but usually we don't have that situation. Usually we don't have the topics and we have to generate the documents. Usually we want to do it the other way around. So we have the documents and we want to get the topics. And this is done by statistical inference. So the idea is that we have to find the best set of latent variables that can explain the observed data. So you could say that we would like to find the model that has most likely generated the documents that we have. Okay, so we were applying this LDA technique to our document collection. And then we got exactly these values for each document that you can see. So how much, how likely or how much of the document belongs to topic 1, how much to topic 2, how much to topic 3, and so on. This means that we get basically a vector for each document with one column per topic and a probability. And what we did then is that we averaged over all documents of one class to get a vector for the whole class in this case. So that's what we've done now. And now we use this to extract first topics that are characteristic for all classes. So this would be the ones that you have here in the middle. This is now what we're interested in first. So how do we do that? Well, we say a topic T is considered to be characteristic for a class if the probability that T is belongs to the class is bigger than 1 divided by the number of topics, and at least X% of the topics of a class contain the topic. Okay, why should the probability be higher than 1 divided by number of topics? Well, simply because this would be the number that we get if the topics were all randomly distributed over our classes. So it should be higher than that. And it should be in at least X% of the documents of a class, because if the term is just very frequent in 1 or 2 documents, then something like term frequency would go up, but this is not what we're interested in. Then we can't say this term is, or this topic is characteristic for the whole set of documents in this collection. And all the topics for which this was the case for all 3 classes, these are the ones that are in the middle here of this intersection. Next, we would like to find discriminating topics. These are now the ones here. And now we say that the topic T is discriminating for a single class, CK, if for all I that are in that set of classes, the probability that T is belongs to class CK is bigger than a discrimination factor times the probability of the next smaller class probability for that topic. and the topic must be characteristic for that class again. So basically we say that the discrimination factor is something that has been given by the user, and we say that it has to be significantly more important, the topic has to be significantly more important for this class than for all the other classes. And finally, we want to get the topics that go in here. And this is now simply the same than under point number 3, just that for the lower of the 2 or 3 classes that we have in the intersection here, we say that the lower probability still has to be higher than the next, significantly higher than the next lower probability that we get. And it has to be characteristic again. And if we do that for our data set, then you get a result like that. And if you look at that now, then I guess you can make much more sense out of it. So in the middle of this triangle here is the topic that all 3 classes share. This is just some words like algorithm, problem, path that give so really just common computer science terms. Then, on the other hand, we have on the top here, by the way, the ones that are blue just belong to SIGGRAPH, the ones that are red just to InfoVis, the green ones just to VIS, and if there are mixed colors, then they belong to the 2 classes that are mapped to that color here. So, for example, the one at the top belongs to InfoVis and VIS and would be in that intersection between the 2 and discriminates it against SIGGRAPH. So this is how you read that. And you can now see that information visualization is basically what discriminates InfoVis and VIS against SIGGRAPH, for example, whereas SIGGRAPH, which is basically a computer graphics conference, has all the terms like is sharing terms like surface, function, mesh, vertex, triangle, points. These 3 topics are shared with VIS. But it discriminates against VIS with respect to BRDF factor, the reflection factor, all this lightning stuff, illumination, but also textures, images, and so on, camera, which is something that is not covered by VIS, but VIS is more on flow visualization, volume visualization, rendering, and so on. And on the other hand, for InfoVis, we have as unique topics the abstract things like graph representations, nodes, treeWIS. The user is very important here, much more important than it is for all the other 2 conferences. And the point that I wanted to make here actually is that using more advanced natural language processing techniques really can help you in your visual document analysis systems. It makes them more powerful, so it's really worth learning a bit about that as well. Okay. Next point is to have compact views for single documents. So far, I've shown you a visualization that was basically visualizing a whole document corpus. What we are now doing is that our focus is more on intermediate level representations for single documents. So what you usually have is you have either these document landscapes on a very high level that gives you an overview, or you have immediately the document itself and the details for that. And this is now about what is in the middle. So to have compact representation of one single document that you can, of course, also use then to get an overview over the collection again. And what was done here is that you generate 1 card per document. And as you can see here, important terms important phrases actually were extracted from the paper, and additionally some pictures of the paper that, well, ideally these should be the pictures that are most expressive and that give you really an idea of what is going on. And in addition, we have the title here and the names of the authors at the bottom, and on the side here you can see some interaction facilities. So for example, if you hover over the title, you get the abstract. If you hover over one of the pictures, you get the caption that is there. You can click on pictures and it zooms moves to the page on which this picture was on. You can also click on all the pages here. You can select a term and see here on the side. It's quite difficult to see, I think, here in that resolution, but you should see here at the side what on which page this term can be found, how frequently. And with such a representation, you can now get nicely also an overview over the whole corpus of documents. There's only one drawback here. This works really nicely for conferences like InfoVis or VASS, but if you do it for like a mathematics conference or, I don't know, psychology, it probably wouldn't work as well. But this is something that we have on the agenda for future work at the moment. So how does do intermediate level representations for those conferences look like?
So the graphics are extracts from the graphics that are in the text?
They are from the paper, directly from the paper.
So perhaps one way of doing that you'd have to think of some potential graphical representations of certain types of concept.
Mm-hmm.
Find those concepts
in
the document, then you could put some sort of graphic in there to say this concept's being discussed in this part.
Mm-hmm. Okay, next point, distribution of text properties across a document. In this case, the application task was authorship attribution. So in authorship attribution, the idea is that you have a set of documents of, in this case, books of author A and a set of books of author B, and you have one book for which the authorship is disputed. So what you want to do is you would like to analyze the writing style of these authors to find out who has written the book, who has most likely written the book of these two. And this has been done many times before, so we were simply looking at the features that have been suggested for that, and then generally the features that are used for that have to be chosen in a way that it's difficult to fake them, okay? Because you have to assume that the author, one of the authors, tries to imitate the writing style of the other author. So obviously, if you know that your colleague is always signing letters with "see you soon," then this wouldn't be a good feature for discrimination here, because you can easily fake that, you can use it yourself. Okay. Simple features are, for example, the average number of syllables per word or the sentence length. Then we can analyze the parts of speech that are used. So, for example, in this case, if we part of speech tag that sentence, then you get what you can see in the upper table here. If you look at the table below there, this is simply the feature that you would get if you would aggregate this, count how often the verb, there was a verb in there, how often the number, and so on, conjunction. Searching would be frequency of specific words, like, for example, function words like the, that, although, however, because, which. This may sound strange at the beginning, but if you think about it for a while, then you may realize that, I mean, almost all people have their favorite function words, actually. So some people tend to write however in every second sentence. The other people take although and so on, and this is really, so that's quite a good discriminating feature, actually. Okay, the next section are the vocabulary richness features. So we would like to analyze now what vocabulary is used here. And again, we, as an example sentence, we have to be or not to be, that is the question. And if you count this, then you have in total 10 different words, or we also call them tokens. But you just have 8 types. Type means that we're just counting the unique words. So in this case, be is there twice, so this is just one type. And by the way, if we had done a lemmatization before that, then is would have been counted as be as well. So this is, again, an example where it makes a difference if you lemmatize words or if you don't lemmatize them. So one suggested feature here was type token ratio, so simply take the ratio between the two. Next one is Simpson's index. What this measure does is that it tries to take the frequency histogram actually into account that you get. So how many words are used once, twice, 3 times, and so on. And then we also included 2 features that the first one, hapax legomena, just takes into account the ratio between the words that are just used once to the overall number of tokens. And hapax dyslogomena does the same with the words that are just used twice, exactly twice. Okay, so if we do that, then we can calculate, we get a lot of numbers for a book. And the question is, what are we going to do with them? Easiest would be to average them, so we get 1 value per document. Then we can, again, compare them. But what if the development over the text is exactly what is discriminating the different authors? So then we need to take that into account as well, and this is what we try to do here. So at the top, you can now see the books of Jack London, and at the bottom of Mark Twain. And this was just an example data set, so I don't know of any book that is disputed between the two. We just wanted to see how well the different features discriminate here. So in that visualization, each of these pixels that you can see represents one text block of 10,000 words. Why is the text block so big? Well, one reason for that is that many of the features that I just explained, you don't work on single sentences. For example, if I just give you one sentence, you can't estimate vocabulary richness. That's just not enough. Oh, and something else that is important to know is that neighboring pixels, they overlap, the text blocks overlap 9,000 words. And this is important to get some smoothing in here to make us split point independent a bit. And these pixels are now grouped into books, so that's a single book that you can see here. And in this case, this is average sentence length. So if you look at that, it's actually able to discriminate quite nicely between the 2 parts. There's only Tom Sawyer sticks out a bit, and Jerry of the Islands as well would fit. So these are now some different features. The one here in the middle is the same that I just showed you. And if you look at that now, then you can should search for features that are able to discriminate the books at the bottom from the ones at the top. So for example, the ones at the top should be all blue and the ones at the bottom all red. And if you take a look at that, then you see that it works quite nicely for some of them. So Simpson's index seems to work at least a bit. The function words do work quite well here at the right side. And one thing that doesn't work at all, for example, is hapax dyslogomena. There it looks, that's the one at the bottom here, sorry. It looks almost randomly distributed. But one other nice thing that we found out is that if you look at that closely, then you can see that there is one book that always sticks out in really a lot of those features, which is Huckleberry Finn of Mark Twain. Seems to be in some kind of different writing style, and yeah, some people say that maybe this is because it has been written in a southern accent, or because he took more time for that or so. It's kind of special for that author. Okay, now I said that we've done that because we wanted to see if distribution maybe plays a role, and we haven't, I mean, our goal also wasn't to do a contribution and author attribution here, but for that example that we did, we couldn't confirm that hypothesis. So here it didn't make much of a difference. I guess we could have used average as well. But this is not always the case. I just want to show you this to make the point that in some cases it does make a difference. So if you look at these 2 books, they both have approximately the same average score for, this is sentence length, I think, again. But if you look at the structure, then you see that there are some clear differences in terms of the distributions of the value. So in the book at the bottom, it's quite consistent over the whole book, the sentence length, whereas in the book at the top, it's jumping between passages with very long sentences and with very short sentences. And if you look into that, then you'll see something interesting, because what Mark Twain did here is that he basically pasted the different things together from he was traveling around and he had to write a book, and the longer the book was, the more he was paid. This was basically the deal. So he took reports of a murder and scientific reports from naturalists and so on, and all pasted them together in his book to get his book longer. And this is what you see here, actually, that there are really, really different writing styles mixed, basically.
So is that sequential across the book?
Yeah. Sorry, I should have said it. Yeah. And now I have a question, because I started 10 minutes later. I won't get through it in 5 minutes. Shall I do it in 5 minutes, or shall I? Because then I have to jump now.
Do it at your own pace.
Okay, I'll try to speed up a bit, but
it's only,
5 minutes is a bit...
it's only coffee we'll miss.
Okay. Then the third part are the relationships within and among the documents. And here I would like to show you 2 examples, and these are actually quite quick, so we're getting close to coffee, I guess. One thing is of Frank Hem et al., and I like it quite a lot because they are doing some really nice and simple analysis of literature. What they do is that in their tool you can search for phrases like word 1 and word 2, word 1 of the word 2, and so on. All these different phrases are extracted, and if they find such a phrase, then in the network that you can see at the side here, then these 2 words would be connected. So for example, here it's word 1 and word 2. This is what we selected here. And this is the structure of, of Jane Austen's Pride and Prejudice. And if you know the story a bit, then you can read something out, like for example, here at the side we have a cluster of the main protagonists. Then here we have like this mother, aunt, uncle, sister cluster. And there are some good sense humor and so on is connected. Yeah, you can simply dig into the literature in that way as well. You can quite find out something. Second example is one that shows you the co-authorship network of an HCI field. And in this case, each node represents a researcher, each node size, the number of articles that this researcher published. The darkness is the number of citations, and links are co-authorship, and link width is proportional to the number of co-author papers that those 2 have. And you can now easily see the dark big ones are basically the key players of the field. I have to admit that I don't know which year this was generated from, but it's now, in this case, it's McKinley, Card, Robertson that are quite big here. We have Schneiderman here. And you can also see something like the collaboration networks here. You can see which persons are tightly connected to other persons. And the main reason why I'm showing you this is also because I want to make 2 points here. First one is, in this case, we were just using metadata of documents, which can be also very important, very interesting. And second thing is, in this case, the data has been structured so much so far that we are now able to use techniques that are not at all specific for document analysis anymore. So you're going to have a presentation on network visualization tomorrow, I think. And I guess that the techniques that you learn here could be perfectly applied to that domain as well, if you really have network structures that you want to take a look at. So in this case, we don't have something that is characteristic just for document visualization. Okay, last point. Temporal trends. And here I want to show you an example in which customer feedback data of an online store was explored. And what they get is they got about 25,000 of those customer feedback comments per year. So this is quite a lot. And what the company is interested in is basically if there are any problems that need to be timely addressed. And what is specific about the data in this case is that we are not only looking at a collection, but we are looking at a stream of data. So they arrive constantly, but at irregular rates. So you never know how many and what documents are coming. In terms of document analysis, we've got two challenges here. So first is sentiment detection. If we want to know what problems are addressed, then we have to find the problems first. We have to identify them with an automatic algorithm. And second thing is that we have to analyze that stream. So we need to detect the relevant issues that need to be taken care of. First point is sentiment detection. So the way that this was done here is that first all nouns were identified using the part of speech tagging that I introduced before. Then the opinion signal words were identified, and this was done with the help of a word list, simply a list of negative terms and a list of positive terms. And again, here it can be important that you have then done lemmatization before, because otherwise you won't find the word in the dictionary. And then, of course, negation has to be taken into account. So we have to invert the polarity of an opinion signal word if it's negated. And now the second part is actually the more difficult one, because now we have to find out which of opinion signal words refer to which noun that we have identified. So, and there are also different ways to do that. So you can say that simply, if I have a noun, then I'm searching for the closest opinion signal word in the sentence, and I'm assuming then that this is what I should map to that word, and this is what was done here. But you could also, in this case, use something like, for example, a dependency parser that gives you the sentence structure and try to take this into account. This is important if you have very long sentences and you know that there are subordinate clauses in the middle, because then the opinion signal word can be far away from the feature that you're looking at from the noun phrase. And the dependency parse would show you that this word refers to the other one. Okay, so let's assume that we now have that. We know for every feature, for every noun that is mentioned there, if it was mentioned positively, negatively, or neutrally. So what we can do next is that in our stream, let's say we are now interested in the term password, then we can throw away all the documents that don't have password in there. Next, we have to think about how we can analyze that stream. So it's for sure that we need some abstraction from that. So let's say that we represent each document now as a bar, and we color the bar according to the sentiment that the word that we're interested in got. If we do so, then we get something like that if we linearly scale that on the timeline. And as you can see here now, that if two documents arrive exactly at the same point of time, then they overlap quite a lot. So we have to deal with that somehow. There are different ways to deal with it. One is simply to put them in a temporal order and forget about the distance that is in between. This saves us much space, but on the other hand, we are interested in problems that are suddenly mentioned much more often than they have been mentioned before, so time is important in this case. And what was suggested here is to have what they call a time density plot. So documents are actually represented exactly the way that I've just shown you, so one behind each other as a bar, but additionally there's this timeline below that. And the timeline, the higher the timeline is, the more dense the documents are in time. So in that example, you can see that C and D arrive at exactly the same point in time. This means that our curve is at a maximum in that position. Whereas between B and C, the distance is very big, and in this case, very big means it's larger than the average distance that we can observe in that stream, and then it would be as low as it can be. Okay. Here's again an example. So that's a real example, the way that it looks in the program. And again, you can see that we have here this overlapping block up there of 27 documents. And then the bottom this would end up here. So you see that the curve is very high and it's staying up because they are very close together. And the bars show you the sentiment, and the height of the bar in this case shows you the uncertainty of the algorithm because this algorithm isn't perfect. Okay, what are we looking for? We are looking for areas like that, for password here in which the curve is very high, although it wasn't as high in the rest of the stream, and where they all are quite negative. And this is what you can see here. And if you read the associated words and you see many email address, not to accept, website, unsuccessful, phone, to try, to fail, and so on. And this was actually a time period in which people couldn't log into the online store. Their passwords weren't accepted, and this is, of course, a problem for the company, and they should make sure that this is taken care of as soon as possible, because otherwise they are losing lots of money. But there's a problem. I told you that we are doing that for every noun that is in this set of 25,000 documents per year. So we end up with quite a lot of nouns, and you surely don't want to go through all of those visualizations. So you would get one line of visualization for each of those nouns. So obviously we need some automatic support here. And this is done by an interestingness function, the definition of which you can see below. So it's a high density curve. We want the curve to be smooth. We want to have a high amount of negative sentiments in there because this is what we are interested in, and a high context coherence among the contained documents. So they are measuring if they are really talking about the same issue in these documents. This was now defined beforehand, and it's hard-coded. But you could also imagine that this is done interactively in the system, and then it would be even a better example for visual analytics, in which you have, again, that feedback loop, and you have a user that can interactively adapt this. And with the help of such an automatic pre-processing and with the help of the interestingness function, they found some more findings. And what is really interesting about them now is that we had only 24 or in the other case 44 occurrences in about 50,000 comments. Okay, so this was a very, very rare term, but still with the help of that technique, you could find out that there's a problem and that this term has to be taken care of in this case. So now at the end, I hope that I could show you that visual analytics is a valuable means to analyze documents or document collections, and also that advanced NLP techniques are really key for good results. And let me add here that I think that visual document analysis is really an exciting and a growing field, and would be happy if more of you decide to work in that field as well.
Thank you very much.